Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches of space where something strange passes through a visitor that shouldn't exist the way it does, carrying ice older than our sun. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The telescopes notice it first as a smudge. Not dramatic, not bright, just a faint elongation in one frame that wasn't there before, moving against the background stars at a speed that makes orbital calculators pause. The designation comes quickly. 3I Atlas, the third confirmed interstellar object. The I stands for interstellar. The Atlas refers to the survey system that caught it, Asteroid Terrestrial Impact Last Alert System, an array in Hawaii built to watch for dangerous rocks. But sensitive enough to catch whispers from beyond, it arrives from the direction of the constellation Camelopardalis, the giraffe. An appropriate irony, perhaps, for something so awkwardly structured. Its trajectory traces back through decades of reverse calculation, through the space between Sirius and Betelgeuse, through regions so empty that hydrogen atoms might drift a meter before encountering a neighbor. It has traveled for tens of millions of years, perhaps longer. The math becomes uncertain when you try to pinpoint which stellar nursery birthed it, which planetary system discarded it into the galactic current. What catches attention isn't the arrival itself. Interstellar objects pass through regularly. Astronomers now understand. Most go unnoticed. The solar system is vast, and these visitors are small, dark, fast. They come, they loop around the sun or merely bend their paths slightly. They leave. The universe is full of orphans. But 3I Atlas begins to glow as it approaches perihelion, its closest point to the sun, and that glow brings scrutiny. The brightening happens because ice sublimates. Frozen volatiles that have remained stable for eons suddenly face the sun's warmth, even at this distance, even beyond Mars. Water transitions directly from solid to vapor. Carbon monoxide follows. The released gas forms a cloud, a coma around the nucleus, scattering sunlight, making the object visible to instruments that would otherwise miss it entirely. This is standard cometary behavior. First-year astronomy students learn this sequence. And yet, the coma doesn't look right. Observers begin comparing images taken days apart. They measure the distribution of light, the way brightness spreads across the pixels. Comets typically show a central condensation brightest at the core, fading smoothly outward. The standard model assumes one solid nucleus, irregularly shaped perhaps, spinning and venting gas from active regions on its surface. One center, one source. But the brightness profile of 3I Atlas suggests something else. Multiple bright regions within the coma. Not just jets, not just asymmetric outgassing, something more fundamental. The first papers are cautious. Scientists use phrases like complex morphology and unusual brightness distribution. They note that resolution is limited, that the object is distant and small, that interpreting structure from brightness alone is fraught with ambiguity. But privately, in emails between observatories, the word spreads it might have more than one nucleus, more than one center, which shouldn't be possible. Not for something that has survived interstellar space intact. The paradox settles in slowly. like cold water seeping into fabric. If 3i Atlas is a rubble pile, a loose collection of smaller bodies held together by mutual gravity, then how did it remain coherent across millions of years? If it's a contact binary, two objects gently fused, then why hasn't it fully merged or separated? If it's simply one fractured body with multiple active venting sites, then why does the light distribution suggest discrete structural components? Only took 4 billion years to raise this particular question. The object itself is silent on the matter. It continues along its hyperbolic trajectory, shedding gas and dust, reflecting sunlight, indifferent to the confusion it generates in the minds of observers. The telescopes track it nightly when weather permits. Spectrometers break its light into constituent wavelengths. Computers model possible configurations. And the core mystery remains: what, exactly, is holding this thing together? There's a comfort in not knowing, perhaps, in encountering something that defies the tidy categories. Space is full of such objects, probably. Most just never come close enough to reveal their strangeness. 3i Atlas happened to arrive when humanity had instruments sensitive enough to notice, happened to brighten enough to warrant close study, happened to show its impossible structure to eyes that could recognize impossibility. A timing coincidence across deep time, which is to say no coincidence at all, just the intersection of readiness and opportunity playing out against the vast statistical backdrop of the galaxy. The observation campaigns continue, data accumulates in archives, and somewhere in that data, encoded in brightness fluctuations and spectral lines, lies the truth about what passes through. Whether anyone will decode it fully remains uncertain. The first thing astronomers measure with precision is the light curve. This is the graph of brightness over time. For a simple rotating object, a potato-shaped asteroid tumbling through space, the light curve shows a regular pattern. Brighter when presenting its wider face, dimmer when edge-on, cycling predictably with the rotation period. The mathematics are elegant. The interpretation is straightforward. Observers can derive shape, spin rate, even surface properties from a well-sampled light curve. 3i Atlas does not provide a clean light curve. The brightness fluctuates irregularly across hours and days. There are peaks and valleys, but they don't repeat with the crisp periodicity that suggests a single solid body turning on a stable axis. Instead, the pattern is complex. Multiple periodicities seem to overlap. Some observers think they detect a primary rotation period of roughly 8 hours. Others argue for 11. Still others suggest the object might be in a tumbling state rotating around multiple axes simultaneously, which would produce exactly this kind of irregular variation. But there's another interpretation. If the object consists of multiple components, whether loosely bound or in a contact configuration, each component might have its own rotation rate, or the entire assembly might wobble. The light curve could be a composite signal, the sum of several simpler patterns layered atop one another. Disentangling these contributions requires data of exceptional quality and duration. The observation window is limited. 3i Atlas is bright enough for detailed study for only a few weeks as it passes through the inner system. After that, it fades. The opportunity closes. Teams across the world coordinate. Observatories in Chile, Hawaii, the Canary Islands. Each adds data points to the growing archive. The light curve fills in, hour by hour, and the irregularity persists. Whatever 3i Atlas is, it's not a simple spinner. The data doesn't fit the standard models. Adjustments are made, parameters are tweaked. Computer simulations attempt to reproduce the observed brightness pattern by varying shape, albedo, rotation state, Some models come close, none fully succeed. There's a particular signature astronomers look for when a comet has multiple nuclei. The coma should show distinct condensations, separate bright regions that correspond to individual outgassing sources. When comet Shoemaker Levy 9 broke apart before impacting Jupiter in 1994, it fragmented into more than 20 discrete pieces, each trailing its own coma. The images were unambiguous, multiple pearls on a string, each bright and distinct. But that fragmentation happened recently, catastrophically, during a close pass by Jupiter. The pieces were separating, spreading apart over weeks and months. The structure was dynamic and temporary. 3I Atlas shows something different. The brightness distribution within its coma suggests multiple active regions. Yes, but their separation is subtle. Not the obvious fragmentation of Shoemaker-Levy, more like a single fuzzy cloud with internal structure, like looking at a distant city through fog and sensing neighborhoods without seeing individual buildings. The interpretation requires inference, assumptions, the willingness to entertain possibilities that strain against conventional understanding. Some researchers propose that what appears to be multiple centers is actually just asymmetric outgassing from a single, highly irregular nucleus. Comets are notoriously lumpy. Their surfaces are mosaics of different ice compositions, dust coverage, topographic features. When sunlight heats particular regions, jets of gas erupt from discrete vents, creating thrust that can alter the object's spin and orbit. These jets can produce complex patterns in the coma, multiple bright spots, asymmetric fans of dust, all from one body. Occam's razor suggests this is the simpler explanation, but Occam's razor doesn't always cut cleanly in astronomy. Sometimes the simplest explanation requires ignoring inconvenient data, and some of the data from 3I Atlas is inconvenient. The spatial separation of brightness peaks seems too large to explain by surface jets alone. The spectroscopic measurements suggest subtly different compositions in different regions of the coma. Not dramatically different, just enough to notice, just enough to wonder whether different components might be venting different ices. The uncertainty settles into the literature like sediment into a lakebed. Papers are published with careful phrasing. The morphology is consistent with either a single nucleus with complex activity or a contact binary system, or a loosely bound binary with separation of several hundred meters. Every base covered, every interpretation acknowledged. The data permits multiple stories, insufficient resolution to choose between them. And perhaps there's something fitting about that? An interstellar visitor maintaining its mysteries even under scrutiny. Only took 100,000 photons to raise all these questions. The object reflects sunlight. The light carries information. The information is encoded in arrival times, wavelengths, intensities. But information is not understanding. Understanding requires context, models, assumptions about how the universe works. And when the object doesn't conform to assumptions, the understanding fragments like ice under thermal stress. The teams continue observing. Larger telescopes are requested. Observing time is competitive, allocated by committees who weigh scientific merit against dozens of competing proposals. 3I Atlas wins some time, loses other bids. The data accumulates unevenly, and the light curve remains stubbornly complex, a graph that refuses to simplify into the clean sine wave that would settle all debate. The problem becomes clearer when astronomers attempt to model what they're seeing. Computer simulations are built to test hypotheses. If the object is a single nucleus, what shape and activity pattern would reproduce the observed brightness? If it's two bodies in contact, what sizes and orientations work? If it's a binary system with physical separation, what orbital parameters match the data? The The simulations run through thousands of iterations, varying parameters, comparing synthetic light curves to real measurements. The single-nucleus models struggle first. To explain the brightness distribution, they require a nucleus with extreme elongation, perhaps 4 or 5 times longer than it is wide, and multiple discrete venting regions positioned at specific latitudes and longitudes. Possible, certainly. Comet 67T Churyumov-Gerasimenko, visited by the Rosetta spacecraft, has a dramatic double-lobed shape and complex outgassing patterns. But Rosetta could image 67P from close range, resolving surface features down to meters. For 3I Atlas, observers work with brightness fluctuations and smudged coma structure, trying to infer solid form from diffuse glow. The contact binary models perform better in some respects. 2 lobes, each with its own composition and activity, joined at a narrow neck. This geometry naturally produces asymmetric brightness as the object rotates, first presenting one lobe, then the other. The light curve becomes a composite of 2 overlapping signals. Some of the observed irregularity makes sense in this framework, but contact binaries require a formation history. 2 separate objects had to encounter each other at extremely low velocity walking speed, essentially and adhere in the outer regions of a protoplanetary disk where planetesimals grow slowly through accumulation. Such gentle collisions are plausible, common even. But 3I Atlas is interstellar. It formed around another star. It was ejected, probably gravitationally scattered by a giant planet, and spent tens of millions of years crossing the space between stars. During that journey, it would have experienced no significant external forces, no tides, no perturbations, just the gentle pressure of starlight and the occasional impact of interstellar dust grains. A contact binary formed in a distant protoplanetary disk could, in principle, survive this journey intact. The question is whether it should. Tidal forces present the first concern. Even the weak gravity between 2 lobes creates stress at the contact point. Over millions of years, does that stress cause further merging? Does the neck thicken as material flows from higher regions to lower, or does it remain frozen, literally, locked in configuration by the cold of space? The physics at these temperatures and timescales is not well understood. Laboratory experiments can simulate cometary ice, but not over millions of years. Not under the exact conditions of interstellar space. Then there's rotation. If 3I Atlas is indeed a contact binary, its rotation imparts centrifugal force. Each lobe experiences an outward pull. For a loosely connected system, this force works to separate the components. Only mutual gravity and structural cohesion resist. The balance between these forces determines stability. Calculations suggest that for the estimated size and mass of 3I Atlas, a contact binary could remain stable if the rotation period is longer than a few hours. The observed period, uncertain as it is, falls near this boundary. Stable, but barely. A configuration that has perhaps been slowly evolving throughout its journey. Some researchers entertain a more radical possibility that 3I Atlas is not a contact binary, but a true binary. 2 separate bodies orbiting their common center of mass with a physical gap between them. Binary asteroids exist in the solar system. They're rare, but documented. Most form through rotational fission. A single object spins fast enough that centrifugal force overcomes gravity, and the body splits. Others might result from gentle captures during formation. Either way, maintaining a binary system over billions of years requires the right combination of orbital parameters, mass ratio, and external perturbations. For an interstellar object, the stability requirements are even stricter. During ejection from its home system, Tidal forces from the giant planet that scattered it would have been immense. Any binary with wide separation would have been torn apart. Only very close binaries nearly touching could survive. And once in interstellar space, the system faces another threat: passing stars. The galaxy is not empty. Every few million years, on average, a star might pass within a light year or so. The tidal force from such an encounter could disrupt a loosely bound binary. Not catastrophically, just enough to pull the components apart into separate interstellar trajectories. Only took one ejection and one journey to test every limit of structural integrity. The object has either beaten the odds or the interpretation is wrong. Both possibilities linger in the data, unresolved. Some researchers favor the contact binary model because it requires fewer unlikely coincidences. Others point out that a single, highly active nucleus remains the simplest explanation and shouldn't be discarded without stronger evidence. The debate continues in academic journals, in conference presentations, in the quiet exchanges between researchers who have spent months staring at the same light curves. There's a certain patience required in astronomy. The objects don't hurry. The data accumulates at the speed of Earth's rotation, the pace of orbital mechanics, the rhythm of telescope scheduling. And sometimes the data simply doesn't yield a definitive answer. Sometimes the universe presents a question and withholds the key to resolution. 3i Atlas may be one of those questions. A puzzle that will remain unsolved not because humanity lacks the intelligence to solve it, but because the information required for solution no longer exists in accessible form. The simulations continue running. Parameters vary, models evolve, and the object itself continues outward, past Mars, past Jupiter, heading back toward the outer system and eventually beyond, carrying its configuration, whatever it truly is, into the dark. To understand why multiple centers shouldn't be possible, it helps to revisit how comets form in the first place. In the cold outer regions of a protoplanetary disk, beyond the frost line where water remains frozen, small particles drift through the thin gas. These are not yet planetesimals, just dust grains, ice crystals, perhaps a few millimeters across. They move on slightly different orbits, colliding gently at speeds measured in centimeters per second. At these velocities, molecular forces become relevant. Van der Waals attraction, electrostatic adhesion, the particles stick. This is the beginning of accretion. One grain plus another becomes two grains bound together. Add a third, a fourth. Over thousands of years, the aggregate grows to pebble size, then boulder size. The process is slow because the disk is sparse and collisions are infrequent. But time is abundant. A protoplanetary disk might persist for several million years before the gas dissipates and accretion ends. During that window, given enough patience and proximity, pebbles can grow into kilometer-scale bodies. These growing objects are not solid in the way rock is solid. They're porous, fluffy, more void than substance. The structure resembles a snowbank more than a stone. Individual grains remain distinct, connected by weak bridges of ice, separated by empty space. The bulk density is low, perhaps a few hundred kilograms per cubic meter, compared to pure water ice at nearly 1,000. This porosity is important. It allows comets to survive impacts that would shatter solid rock. The structure absorbs energy through compaction rather than fracture. As the planetesimals grow larger, their mutual gravity becomes relevant. A kilometer-sized body has enough mass to gravitationally influence nearby objects. Small pieces in the vicinity begin to drift inward, drawn by gravity rather than random collision. The accretion rate increases. The largest bodies grow fastest, sweeping up material from wider regions. This is the runaway phase of planetary formation. It produces a population of differentiated sizes, a few large bodies and many smaller fragments. But the outer disk is not uniform. Different regions have different temperatures, densities, compositions. The balance between carbon monoxide ice, water ice, and ammonia ice varies with distance from the star. Objects forming in slightly different locations carry subtly different chemical signatures. If two such objects later collide and merge, the resulting body retains compositional heterogeneity. One region might be richer in carbon monoxide, another in water. The chemistry is frozen in place, literally preserved by the cold. This is how contact binaries might form two independently growing planetesimals, each a few hundred meters across, drift toward each other under mutual gravity. The collision happens at perhaps a meter per second, barely a collision at all, more like a docking. The surfaces compress slightly. Ice grains interlock. The two bodies settle into a stable configuration, joined at the contact point, rotating slowly together. Over time, this might be the most common outcome for small planetesimals in the outer disk, not single spheres, but aggregates, clusters, piles of loosely connected components. The Rosetta mission confirmed this picture when it reached Comet 67P in 2014. The comet clearly showed a bilobed structure, two distinct masses joined by a narrow neck. High-resolution images revealed layering in both lobes, different surface textures, variations in ice composition. The interpretation two separate objects that merged early in the solar system's history then remained paired for 4.5 billion years. If 67P can maintain such a structure across the age of the solar system, then perhaps 3I Atlas, formed similarly around another star, can do the same. But 67P orbits the Sun. It experiences solar heating during perihelion passage, losing mass through sublimation, but it always returns to the cold outer system where the ice stabilizes. It's never been ejected into interstellar space, never faced the cosmic ray bombardment, the isolation, the gradual erosion of volatiles into the near vacuum. 3I Atlas has endured all of this. Whether that makes it more or less likely to maintain structural complexity is an open question. Some researchers point out that the interstellar environment might actually preserve structure better than a typical cometary orbit. No repeated heating cycles, no thermal stress from perihelion passages, just steady cold, a few degrees above absolute zero, for millions of years. In that environment, ice behaves almost like rock, rigid, unchanging. The contact point between two lobes would remain frozen exactly as it was at formation. No flow, no relaxation, just preservation. Only took 30 million years of nothing happening to keep everything the same. The irony of deep time that stability and change operate on such different scales. Human lifetimes are too brief to witness geological or astronomical processes directly. Everything significant seems to happen either instantly, supernovae, impacts, or across spans so vast they blur into timelessness. The slow transformation of a contact binary. The gradual merging of two lobes. The patient redistribution of ice from one region to another. These processes might take longer than the object has existed. So perhaps 3I Atlas is simply caught in mid-formation, not fully merged, but on its way. A snapshot of a transition state that will eventually resolve into a single unified nucleus given another 100 million years. Or perhaps it's already at equilibrium, as merged as it will ever get. A stable configuration that could persist indefinitely. The data doesn't distinguish between these narratives. Both are consistent with what's observed. Both involve enormous stretches of time made invisible by the collapse of causation into a single moment of observation, now, as the object passes through the inner solar system, briefly bright, briefly scrutinized. The formation models sit in the literature, invoked when needed, adjusted when observations demand it, and the actual object continues along its path, formed however it was formed, shaped by processes that occurred before Earth had continents, around a star whose identity remains unknown. The rubble pile hypothesis emerged in the 1970s and 1980s as astronomers began to understand that many small bodies in the solar system are not monolithic. They're gravitationally bound collections of fragments, held together by their mutual attraction rather than material strength. The realization came partly from observations of asteroid densities many were far too low to be solid rock, and partly from modeling catastrophic collisions. When a large asteroid is struck hard enough to shatter, the fragments don't necessarily disperse. If the impact energy is below a certain threshold, gravity reassembles the pieces into a loose aggregate. These rubble piles have strange properties. They can withstand impacts that would destroy solid bodies because the structure absorbs energy through rearrangement. A projectile striking a rubble pile compresses the local region, shifts individual components, but doesn't propagate fractures through the whole mass. There's nothing to fracture. The body is already fragmented. This makes rubble piles surprisingly resilient. They can survive collisions, tidal encounters, even close passes by planets that would tear apart a solid object. But rubble piles also have limitations. The individual components must remain within the mutual gravity well. For small bodies, this well is shallow. A fragment ejected at even a few meters per second might escape entirely. This means rubble piles are dynamic systems. Material shifts, components settle into lower energy configurations. Over time, the structure evolves toward a more compact, more spherical shape as gravity works to minimize gravitational potential energy. The process is slow, but relentless. For a rubble pile to maintain distinct multiple centers, separate concentrations of mass within the overall gravitational envelope requires a specific configuration. The centers must be large enough to resist gravitational settling into a single merged body, yet close enough to remain gravitationally bound. The margins are narrow, too close, and they merge, too far apart, and they separate. The equilibrium exists only within a tight range of parameters that depend on size, density, rotation rate, and the strength of the material itself. Cometary ices complicate the picture. Ice has material strength, not much, but some. At the temperatures of interstellar space, a few dozen Kelvin above absolute zero water ice becomes quite rigid, more like rock than snow. This strength allows cometary nuclei to maintain irregular shapes despite rotation and tidal stress. The ice doesn't flow easily at these temperatures, doesn't compact or deform under its own weight. A comet nucleus might remain effectively frozen in its initial configuration for billions of years, preserved by cold the way amber preserves insects. But if 3I Atlas is a rubble pile, then it consists not just of ice, but of multiple discrete chunks, each presumably several tens or hundreds of meters across, orbiting their common center of mass while nearly touching. The gaps between components might be centimeters or meters. The boundaries are fuzzy because each component trails its own tenuous atmosphere of sublimating ice. The mutual gravity is weak. The orbital velocities are measured in centimeters per minute. This is not a binary system in the classical sense, with distinct separation and clear orbital mechanics. It's more like a cloud held together by gossamer threads of gravitational attraction. Maintaining such a configuration over millions of years requires almost perfect isolation. Any external perturbation could disrupt it. A close stellar passage, an impact by interstellar dust grains massive enough to impart significant momentum. Even the gentle pressure of starlight, acting over vast time scales, might be sufficient to alter the delicate balance. The fact that 3I Atlas arrives in the inner solar system with a potentially multi-centered structure suggests either extraordinary luck or a more stable configuration than intuition suggests. Some researchers argue that what appears to be multiple centers might actually be internal structure within a single body. A rubble pile with a few large components embedded in a matrix of smaller fragments. From the outside, observing only brightness and outgassing patterns, this could mimic the signature of multiple discrete nuclei. The distinction becomes semantic. At what point does a collection of fragments constitute one object versus several? If they're gravitationally bound and move as a unit, conventional taxonomy calls that one comet. But if internal structure is strong enough to maintain distinct regions with different properties, the boundary blurs. Only took 1 billion collisions to create something this ambiguous. The early protoplanetary disk was a chaotic environment. Planetesimals formed, grew, collided, shattered, reaccreted. The process repeated countless times. Each cycle left traces compositional layering, fractured interiors, irregular shapes. The objects that survived to be ejected into interstellar space carried this history embedded in their structure. Reading that history from brightness fluctuations is like trying to reconstruct a manuscript from shadows. There's a certain elegance to rubble piles. They represent gravitational collapse in its gentlest form, not the catastrophic infall of gas into a star or the compression of matter into planetary cores, but the quiet accumulation of already formed pieces into a loosely organized whole. The universe seems fond of this pattern. Galaxies are rubble piles of stars. Globular clusters are rubble piles of ancient suns. Planetary rings are rubble piles of ice and rock. At every scale, gravity collects fragments and holds them in tenuous embrace. Whether 3I Atlas is such a collection or merely resembles one remains uncertain. The observations don't provide sufficient resolution. The models can't eliminate alternatives, and so the object occupies a superposition of interpretations, simultaneously one thing and several, until some future measurement collapses the uncertainty. But that measurement may never come. The object fades. The observation window closes. And the question remains suspended in astronomical literature, waiting for the next interstellar visitor to either confirm or contradict the pattern. Tidal forces grow stronger as objects approach massive bodies. This is basic orbital mechanics, encoded in Newton's law of universal gravitation. The force of gravity decreases with the square of distance, which means the near side of an extended object feels stronger attraction than the far side. This differential force, the tidal force, stretches the object along the line, connecting it to the massive body. For small differences in distance, the effect is negligible. But as separation decreases or object size increases, tides become significant. The Roche limit defines the critical distance. Inside this boundary, tidal forces overcome the self-gravity holding an object together. A rubble pile entering the Roche limit begins to elongate. Components on the near side accelerate forward. Components on the far side lag behind. The structure stretches like taffy until it fragments into a stream of debris. This is what happened to Comet Shoemaker-Levy 9 during its close pass by Jupiter in 1992. The comet crossed Jupiter's Roche limit and shattered into more than 20 pieces, which then continued independently until they impacted the planet 2 years later. For 3I Atlas to maintain multiple centers, whether as a contact binary, a rubble pile, or any loosely connected configuration, it must never have crossed the Roche limit of any massive body during its journey. This seems obvious. An object that fragments during ejection wouldn't survive as a coherent unit. But the constraint is stronger than it first appears. During the ejection process itself, the object must have passed very close to a giant planet, close enough for gravitational scattering to alter its trajectory from bound orbit to escape velocity, close enough that tidal forces would have been substantial. The calculations depend on the specific geometry of the encounter. An object passing behind a planet in the direction of the planet's orbital motion experiences a gravitational assist that increases its velocity. If this boost is sufficient, if the object is moving fast enough and close enough, it can reach escape velocity and leave the planetary system entirely. But the distance of closest approach matters enormously. Too close, and tides dominate. Too far, and the velocity increase is insufficient for ejection. The viable zone is narrow. For a contact binary or loosely bound system to survive this ejection, it must pass through the narrow zone at exactly the right distance. Close enough for ejection, but not so close that tidal forces tear the components apart. The probability of threading this needle is low, but not zero. And given the vast number of comets in the outer regions of planetary systems, billions, perhaps trillions, even low probability events occur regularly on galactic timescales. Rare outcomes become inevitable when the sample size is infinite. Once ejected into interstellar space, the tidal threat diminishes dramatically. The nearest massive bodies are other stars, light years away. At those distances, tidal forces are essentially negligible. A comet drifting through interstellar space experiences almost no external gravitational influence. No tides, no perturbations, just isolation. This is the environment where a fragile multi-component structure might survive indefinitely, protected by emptiness. But stars move. The galaxy rotates differentially, meaning stars at different distances from the galactic center orbit at different speeds. Over millions of years, stars that were once distant neighbors pass close to one another. Most stellar encounters remain distant several light years of separation, but occasionally, two stars pass within a light year or less. During such encounters, comets in interstellar space can experience measurable tidal forces, not enough to immediately disrupt a nucleus, but enough to perturb orbits, alter rotation states, perhaps stress weakly bound structures. The statistics of stellar encounters are well studied. For a typical trajectory through the galactic disk, an interstellar object might experience a close stellar passage every few million years on average. The cumulative effect over tens of millions of years becomes significant. Each encounter applies stress. Each stress tests the structural integrity of the object. For a single monolithic nucleus, these stresses are irrelevant. But for a multi-component system held together by weak gravity, each encounter is a trial. Survive enough trials, and the structure proves its stability. Fail once, and the components separate forever. Only took 10 million years of stellar roulette to reach the inner solar system. The object has either been extraordinarily fortunate or its structure is more robust than the simplest models suggest. Perhaps the components are not loosely bound, but actually in contact, joined by material strength as well as gravity. Perhaps the ice has sintered over time, fusing at contact points through molecular diffusion. Perhaps the configuration is inherently stable in ways that aren't captured by models, assuming purely gravitational binding. There's also the question of what happens upon arrival. 3I Atlas is now experiencing tidal forces from the Sun. At perihelion, its closest approach, these forces are substantial. Not enough to disrupt a kilometer-scale object, but certainly enough to stress any weak points in the structure. If the object is a contact binary, the sun's tides work to separate the lobes. If it's a rubble pile, the tides try to pull components apart. The fact that the object remains coherent during this passage suggests either strong binding or fortunate geometry. Some researchers calculate that 3I Atlas passes well outside the sun's Roche limit for cometary material. The limit depends on density. Lower density means a larger Roche radius, but for reasonable assumptions. The critical distance is perhaps a few solar radii. 3I Atlas reaches perihelion at roughly 2 astronomical units, more than 400 solar radii. Safely distant. The tidal forces are present, but not catastrophic. A structure that survived ejection and interstellar transit should survive this final passage as well. And yet, the uncertainty persists. Do the observations really show multiple centers? Or is that an artifact of viewing geometry and asymmetric outgassing? Is the structure fragile or robust? Is the configuration ancient or recent, the result of formation or of fragmentation? The tidal history of the object, where it's been, what forces it's experienced, is written in its current state, but the language is ambiguous. The data permits multiple readings, and without higher resolution observations or a sample return mission, which is entirely infeasible for an interstellar visitor on a hyperbolic trajectory, the ambiguity remains. The object continues outward. The sun's gravity weakens. Tidal forces diminish, and whatever configuration 3I Atlas possesses, it will carry that configuration back into the vast dark between stars, where nothing will stress it again for millions of years. The outgassing begins when sunlight warms the surface, even at great distances from the sun. Even where temperatures remain far below freezing by terrestrial standards, the transition from interstellar cold to even modest solar heating represents a dramatic change. Ices that have remained stable at 10 or 20 Kelvin suddenly face temperatures of 80, 100, eventually 150 Kelvin as the object approaches perihelion. The most volatile ices respond first. Carbon monoxide sublimates at very low temperatures. Well, before water ice begins to vaporize, carbon monoxide transitions directly from solid to gas, bypassing the liquid phase entirely. This is sublimation. The molecules gain enough thermal energy to break free from the ice matrix and escape into space. The process creates pressure beneath the surface. Gas accumulates in pores and voids, seeking paths to the exterior. When it finds a weakness, a crack, a region of lower density, a boundary between ice layers, the gas erupts as a jet. These jets are not dramatic in the Hollywood sense. No roaring flames or explosive violence, just steady streams of vapor and entrained dust particles, venting into vacuum at perhaps a few hundred meters per second. The gas expands rapidly in the near vacuum of space, forming a coma around the nucleus. Dust particles, lifted by the gas flow, scatter sunlight and make the coma visible. This is what transforms a dark, inert object into a visible comet. The coma can extend for thousands of kilometers, vastly larger than the nucleus itself. For 3I Atlas, the outgassing begins beyond Mars orbit. This is earlier than typical for solar system comets, which often activate only inside the asteroid belt. The early activation suggests high carbon monoxide content. Spectroscopic observations confirm this. The light from the coma, when dispersed into its constituent wavelengths, shows strong emission lines from carbon monoxide molecules. Water is also present, but carbon monoxide dominates. This composition is unusual compared to most solar system comets, which tend to be water-rich. The difference might reflect formation environment. If 3I Atlas formed in a colder region of its protoplanetary disk than typical solar system comets, farther from its parent star, then carbon monoxide ice would have been more abundant. Or perhaps the star itself was cooler, allowing carbon monoxide to condense at smaller orbital distances. Or perhaps the disk chemistry was simply different, reflecting different initial abundances of carbon and oxygen in the stellar nebula. Each possibility points to a formation history distinct from solar system objects. But the composition also complicates the structural question. If different regions of the nucleus have different ice compositions, one region rich in carbon monoxide, another in water, they will outgas at different temperatures. The carbon monoxide-rich region activates first, while the water-rich region remains dormant. This could create the appearance of multiple active centers even if the nucleus is structurally unified. The brightness distribution in the coma would show distinct condensations corresponding to different compositional zones. Observers attempt to map the outgassing patterns by tracking brightness changes over the rotation period. If specific surface features rotate into sunlight and then into shadow, the outgassing should vary accordingly. Active regions should brighten when sun-facing and dim when in shadow. By monitoring these variations, astronomers can infer the locations of vents on the nucleus surface. For 3I Atlas, the data suggests at least 2 major active regions, possibly more. Whether these are separate components or just compositionally distinct areas on a single body remains ambiguous. The jets also create thrust. When gas vents from the surface, it carries momentum. By Newton's third law, the escaping gas pushes the nucleus in the opposite direction. For a small body with low mass, this non-gravitational force can be significant. It alters the orbit slightly, causing deviations from the purely gravitational trajectory. Astronomers measure these deviations by tracking the comet's position over time and comparing it to predictions. The discrepancies reveal the strength and direction of the outgassing thrust. For 3I Atlas, the non-gravitational forces are measurable but not extreme. The object is being pushed, slightly, by its own outgassing. The direction of the push depends on where the jets are located and how the nucleus is oriented. If the jets are asymmetrically placed more active on one hemisphere than the other, the thrust becomes a net force rather than cancelling out. This can also affect rotation, either spinning the object up or slowing it down depending on jet geometry. Only took 1 billion years of frozen silence to suddenly start hissing gas into space. The transition from dormant ice to active comet happens over weeks as the object approaches the sun. It's a temporary state. After perihelion, as the comet recedes, temperatures drop. Outgassing slows, eventually stops. The coma dissipates. The object returns to darkness. For 3I Atlas, this active phase represents perhaps a few months of its multi-million-year journey, a brief moment of visibility between long spans of invisibility. Some researchers study the dust-to-gas ratio in the coma. How much solid material is lifted compared to the gas flow? For typical comets, the ratio varies widely depending on composition and structure. Dusty comets can have ratios exceeding unity, meaning more mass leaves as dust than as gas. Clean, icy comets might have ratios well below unity. For 3I Atlas, preliminary estimates suggest a moderate ratio. Not exceptionally dusty, but not pure ice either. Somewhere in between. A texture like dirty snow, perhaps. Or sandy ice. The dust particles themselves carry information. Their sizes, shapes, and compositions reflect the matrix from which they were liberated. Large particles fall back to the surface quickly. Unable to escape the nucleus's weak gravity, small particles are carried away by the gas flow. eventually dispersing into interplanetary space. The size distribution tells a story about the strength of the ice matrix, the depth of the dust layers. The history of processing the surface has undergone, but gathering this data requires close observation, high-resolution imaging, spectroscopy of both gas and dust, multiple observation campaigns coordinated across wavelengths. For 3 Atlas, the data remains sparse. The object is distant, faint, and moving quickly. Each observation is hard-won, and each observation raises as many questions as it answers, adding detail to the mystery without resolving the fundamental question of structure. The chemistry of ancient ice carries signatures of its birthplace. When water, carbon monoxide, methane, and ammonia condense from the gas phase in a protoplanetary disk, they trap other molecules and atoms in the ice matrix. These inclusions reflect the temperature, pressure, and chemical environment at the moment of freezing. The ratios between different isotopes, carbon-12 versus carbon-13, oxygen-16 versus oxygen-18, vary depending on formation conditions. The presence of trace species like formaldehyde or hydrogen cyanide hints at specific chemical pathways active in the disk. For solar system comets, decades of spectroscopic observation have established baseline compositions. Most show roughly similar patterns. Water dominates, with carbon dioxide, carbon monoxide, methane, and ammonia as secondary components. The isotopic ratios cluster within a narrow range. Some comets are richer in certain volatiles than others, suggesting formation at different distances from the Sun. But the overall chemistry is recognizably uniform. These are siblings, born from the same stellar nebula, shaped by the same solar environment. 3I Atlas shows differences. The carbon monoxide to water ratio is higher than typical solar system comets, not dramatically higher, but measurably so. The spectral lines suggest the presence of molecular species in proportions that don't quite match the solar system template. These are subtle distinctions, at the edge of measurement precision, but they persist across multiple observations. The chemistry is not alien. These are the same molecules, governed by the same physics, but the proportions hint at formation under slightly different conditions. Perhaps the parent star was a different spectral type. A K dwarf instead of a G dwarf, cooler and redder than the Sun. In such a system, the frost line, the distance beyond which water ice remains stable, would be closer to the star. The region where comets form might have different temperatures, different densities, different exposure to stellar radiation. These conditions would leave imprints in the ice chemistry, subtle but persistent across billions of years. Or perhaps the disk itself had a different initial composition. Stars form from collapsing molecular clouds, and these clouds are not chemically homogeneous. Some regions are enriched in heavy elements by prior generations of stellar nucleosynthesis. Others are more pristine, closer to the primordial hydrogen and helium ratios. A comet forming in a metal-poor region might have different oxygen isotope ratios. One forming in a metal-rich region might show enhanced carbon or nitrogen abundances. The periodic table, shuffled and redistributed by stellar death and rebirth, deals different hands to different star systems. The spectroscopic measurements from 3I Atlas are not detailed enough to pin down these differences with certainty. The object is too faint, too distant, the observation windows too brief. Observers extract what information they can from the available light, but the signal-to-noise ratios are marginal. Some spectral features are clear, others are ambiguous, possibly present, or possibly just noise. The analysis proceeds cautiously, with error bars that often span the range of plausible values, But even with these uncertainties, the pattern is suggestive. 3I Atlas does not match solar system comets exactly. The chemistry is foreign in subtle ways. This is expected, of course. An interstellar object should carry the chemical signature of another stellar system. The surprise would be if it matched perfectly, which would suggest either extraordinary coincidence or misidentification of the object as interstellar. The differences confirm what the trajectory already indicated this object formed elsewhere. Some researchers use the chemistry to constrain formation models. If the carbon monoxide abundance is high, formation likely occurred beyond 10 or 15 astronomical units from the parent star, in the cold outer reaches where carbon monoxide ice is stable. If certain isotopic ratios match those seen in the local interstellar medium, the parent molecular cloud might have been similar in composition to the solar system's birthplace. Each chemical clue narrows the possible formation scenarios, gradually building a profile of the distant system that gave birth to this wanderer. Only took 4.6 billion years of stellar chemistry to produce ice with this particular recipe. The universe cycles matter through stars, supernovae, molecular clouds, disks, planets, back to stars again. Each cycle adds layers of processing. Heavy elements created in stellar cores are expelled, mixed into clouds, incorporated into new generations of stars and planets. The atoms in 3I Atlas have been through this cycle multiple times. They were hydrogen and helium in the early universe, fused into carbon and oxygen in ancient stars, scattered into space, reassembled in a molecular cloud, incorporated into a protoplanetary disk, frozen into ice. Now they sublimate near our sun, briefly visible, before continuing their journey. There's a particular poignancy to studying the chemistry of an object that will never be seen again. The spectroscopic observations capture a snapshot, a momentary record of composition that represents billions of years of chemical evolution. Once 3I Atlas leaves the inner solar system and fades from view, this record becomes permanent. Future observers might revisit the archived data, reanalyze it with better models or computational tools, extract new insights, but no new observations will be possible. The light captured during this apparition is all that will ever exist. Astronomers are familiar with this constraint. Most celestial objects are observed remotely, across vast distances, with no possibility of direct sampling. The entire field of astrophysics is built on inference from light-extracting composition, temperature, density, motion from the properties of electromagnetic radiation. For nearby solar system objects, spacecraft missions can provide direct measurements, ground truth for calibrating remote observations. But for interstellar visitors, light is the only messenger. And light, for all its information content, still leaves questions unanswered. The chemistry of 3I Atlas remains incompletely characterized. Some molecules are clearly detected. Others are suspected but unconfirmed. The isotopic ratios are suggestive but not definitive. And the question of whether different regions of the nucleus have different compositions, whether the potential multiple centers correspond to compositionally distinct regions, cannot be answered from the available spectra. The data hints, implies, suggests, but does not resolve. The contact binary hypothesis requires a particular kind of collision history. Two objects must approach each other at extremely low relative velocity, slow enough that their combined kinetic energy is less than the gravitational binding energy that would hold them together. This is delicate. Too fast, and they bounce apart or shatter. Too slow, and they never meet. The velocity window exists, but it's narrow, perhaps a few meters per second at most, for objects a few hundred meters across. In the outer regions of a protoplanetary disk, these conditions naturally arise. The gas component of the disk dampens orbital eccentricities through drag. Planetesimals settling into circular orbits around the star have very similar velocities. When two objects on nearby orbits encounter each other, their relative velocity is low. They drift together rather than colliding. The meeting is gentle, surfaces touch, ice grains interlock, gravity takes over. The two bodies become one system, rotating slowly around their common center of mass. This process might be common. Many asteroids and comets in the solar system show bilobed shapes suggestive of contact binary origins. Comet 67P, visited by Rosetta, is the clearest example. Two distinct lobes, each with its own layering and structure, joined at a narrow neck. The Kuiper Belt object Arrokoth, imaged by New Horizons during its extended mission, shows an even more pronounced contact binary configuration, two flattened lobes barely touching, like a snowman built from pancakes. These objects demonstrate that gentle mergers occur and that the resulting structures can remain stable for billions of years. But stability in the solar system is not the same as stability during interstellar transit. Objects orbiting the Sun remain in a relatively constant gravitational environment. They experience perturbations from planets, tidal forces during close approaches, but these are predictable and periodic. An object ejected into interstellar space faces a different regime. The gravitational environment becomes nearly null. No central star, no planetary system. Just the weak, distant influence of passing stars and the galactic tide itself. In this environment, a contact binary might actually be more stable than it would be in orbit. There are no repeated tidal stresses from perihelion passages, no thermal cycling that expands and contracts the ice, potentially weakening the connection, just steady cold and isolation. The neck joining the two lobes remains frozen in configuration, neither strengthening nor weakening, preserved exactly as it was at formation. In principle, such a structure could persist indefinitely. But formation alone doesn't explain how a contact binary survives ejection. The scattering event that sends an object into interstellar space involves a close gravitational encounter with a giant planet. During this encounter, tidal forces are significant. A loosely bound system might be torn apart before it ever leaves the planetary system. Only contact binaries with sufficiently strong connections at the neck would survive. The ice must have structural integrity. The contact area must be large enough to resist the differential forces. The geometry must be favorable, perhaps with the neck oriented perpendicular to the tidal force during closest approach. The statistics are unkind. Most contact binaries probably don't survive ejection intact. They fragment during the scattering process, becoming multiple separate objects on different interstellar trajectories. But some fraction, perhaps a few percent, perhaps less, have the right combination of strength and geometry to remain bound. These survivors become the interstellar contact binaries, carrying their dual structure out into the galaxy. 3i Tau Atlas, if it is indeed a contact binary, belongs to this select population. Only took one successful ejection out of perhaps millions of attempts. The outer regions of planetary systems are graveyards of failed ejections. Comets scattered inward by Neptune or Jupiter, only to fall back into the Oort cloud or impact the Sun. Comets deflected but not ejected, settling into long-period orbits that will eventually decay. Comets that fragmented during close passes, their components dispersing into the planetary system as meteoroid streams. For every object that successfully escapes into interstellar space, countless others fail. The galaxy is populated by survivors, and survivors are rarely typical. Some researchers model the structural strength required for survival. Ice at cometary temperatures has a tensile strength of perhaps a few hundred kilopascals, comparable to weak concrete. If the contact area between lobes is large relative to the tidal stress, the neck can hold. But if the neck is narrow or the tidal stress is extreme, fracture occurs. The calculations depend on unknowable details: the exact shape of the neck, the porosity of the ice, the presence of dust or rock that might strengthen the matrix. The models can bracket the possibilities but can't predict specific outcomes. There's also the question of what a contact binary looks like from a distance. If the two lobes are similar in size and composition, the light curve should show a double-peaked pattern as the object rotates, presenting first one lobe, then the other. If the lobes are different, one larger or more reflective, the peaks would be asymmetric. For 3I Atlas, the light curve is complex, possibly consistent with a contact binary, but also consistent with other configurations. The ambiguity persists. High-resolution imaging would resolve the question immediately. If 3I Atlas could be imaged at scales of tens of meters, the structure would be clear. But such resolution requires either very large telescopes or very close proximity. Ground-based telescopes, even the largest, cannot resolve detail finer than a few hundred kilometers at the distance of 3I Atlas. Space telescopes like Hubble have slightly better resolution, but still insufficient for definitive structural imaging. A spacecraft mission would provide the answer, but organizing and launching such a mission takes years. By the time it could be attempted, 3I Atlas would be too far, too faint, unreachable. So the question remains suspended. Is it a contact binary? The observations permit it. The physics allows it. The formation pathways exist. But certainty is absent, and in the absence of certainty, the scientific literature fills with conditional statements, hedged conclusions, carefully worded abstracts that acknowledge all possibilities without committing to any. This is the appropriate response to insufficient data. But it leaves the human mind unsatisfied, wanting resolution, wanting the story to have an ending. The object continues outward. Its structure, whatever it is, remains unchanged by observation, and the scientific community moves on to the next object, the next measurement, the next attempt to wring understanding from light. The rotation of 3I Atlas complicates every measurement. As the object spins, different portions of its surface come into and out of view. The brightness changes. The outgassing rate varies as active regions rotate into sunlight or into shadow. The spectral signature shifts as different compositions present themselves to the observer. Every measurement is time-dependent, and without knowing the exact rotation state, interpreting those measurements becomes an exercise in disentangling overlapping signals. Initial estimates suggest a rotation period somewhere between 8 and 11 hours. This is derived from the quasi-periodic variation in brightness, but the period is not clean. The light curve doesn't repeat exactly from one cycle to the next. Some peaks are higher, some valleys deeper. The pattern suggests either a complex shape, not simply ellipsoidal, but irregular, with multiple lobes or protrusions, or a tumbling rotation state where the object spins around more than one axis simultaneously. Tumbling is rare, but not impossible. It typically occurs after an asymmetric collision or when outgassing jets create torques that push the rotation away from a stable single-axis spin. A body in a simple spin state rotates around its axis of maximum moment of inertia, the axis that minimizes rotational energy for a given angular momentum. This is stable. Small perturbations damp out. But if the angular momentum vector doesn't align with the principal axis, the object tumbles, wobbling like a poorly thrown football. For 3i Atlas, if the object is indeed a contact binary or multi-component system, the principal axis might be unusual. A dumbbell-shaped body, for example, has its maximum moment of inertia perpendicular to the long axis. If it's spinning end over end, that's a stable configuration. But if it's spinning around the long axis, like a propeller, that's unstable. Small perturbations from outgassing could push it into a tumbling state. The complex light curve might reflect this tumbling, the object presenting different aspects to the observer in an irregular pattern that only repeats over many rotation cycles. Determining the true rotation state requires data spanning multiple weeks. Observers need to track the brightness continuously, or nearly so, to capture the full pattern. But observing time is limited. Telescopes must be shared among many projects. Weather interrupts observations. The moon's phases limit dark time. The data comes in fragments. Gaps between observations where the rotation state evolves unseen. Reconstructing the full picture from these fragments is difficult, requiring sophisticated analysis and modeling. Some teams apply Fourier analysis to the light curve, decomposing the complex signal into a sum of simpler periodic components. If successful, this reveals the fundamental frequencies present in the data, perhaps a primary rotation period, a secondary wobble, a tertiary nutation. Each frequency corresponds to a physical process, the spin rate, the precession rate, the flexing of a non-rigid body. But the technique requires high-quality data and clear signals. For 3i Atlas, the noise level is high and the signals are marginal. The Fourier decomposition produces results, but the uncertainties are large. Other researchers use shape modeling. They assume a particular geometry, an ellipsoid, a contact binary, a rubble pile, and simulate how such an object would appear as it rotates. The synthetic light curve is compared to the real data. Parameters are adjusted to improve the fit. This is an inverse problem inferring three-dimensional structure from one-dimensional time series data. Such problems are notoriously under-constrained. Many different shapes can produce similar light curves. Additional constraints are needed. Spectroscopy, polarimetry, multi-wavelength observations. Each adds information, narrows the possibilities. Only took 10,000 photons to make everything uncertain. Light carries information, but information requires interpretation, and interpretation requires assumptions. The chain from photon to understanding is long and fragile. Each step introduces uncertainty. The photon might be from reflected sunlight or from scattered light in the coma. The brightness might vary due to rotation or due to changing outgassing rate. The shape might be irregular, or the surface might have albedo variations. All these factors mix together in the observed light curve, inseparable without additional data. There's also the question of whether the rotation rate is changing. Outgassing jets create torques. If the jets are asymmetrically placed or variably active, they can spin the object up or slow it down. For some comets, this effect is measurable. The rotation period changes noticeably over weeks or months. For 3i Atlas, the observation baseline is too short to detect such changes definitively, but hints appear in the data. The brightness maxima don't quite occur when predicted. The phase seems to drift slightly. Whether this is real or just noise remains unclear. If the rotation is changing, that provides a constraint on the outgassing distribution. The torque depends on where the jets are located relative to the center of mass and how strong they are. By measuring changes in rotation, researchers can infer jet locations. This is how some teams have mapped active regions on other comets. But for 3I Atlas, the signal is weak. The rotation change, if real, is small. The uncertainties overwhelm the measurement. The technique that works for bright, well-observed comets fails for a distant, faint interstellar visitor. Polarimetry offers another tool. Light reflected from a surface becomes partially polarized, and the degree of polarization depends on surface properties, the roughness, the particle size distribution, the composition. By measuring polarization as the object rotates, observers can infer how these properties vary across the surface. Dust-rich regions polarize light differently than clean ice, smooth surfaces differently than rough, for 3I Atlas. Polarimetric observations have been attempted but are challenging. The object is faint. Polarization signals are small, typically a few %. Extracting reliable measurements requires specialized instruments and careful calibration. The data trickles in slowly. Each observation adds a few data points to the growing archive. The rotation period estimate refines slightly, from 8 to 11 hours initially, then narrowing to 9 to 10 hours, then a best estimate of 9.3 hours, with uncertainty of plus or minus 40 minutes. Still not precise enough to predict the light curve weeks in advance, still not definitive enough to rule out tumbling or precession, still leaving room for multiple interpretations of structure and shape. And the object continues spinning as it recedes. The rotation that began billions of years ago, in the protoplanetary disk of another star, continues unchanged by observation. The angular momentum is conserved. The spin persists. And somewhere in that spin, encoded in the pattern of brightness variation, lies the answer to the question of structure. But the answer remains encrypted, waiting for a decoder that may never arrive. The density of a comet nucleus tells a story about its interior. A high-density object is compact, with minimal void space. A low-density object is porous, more air than substance. For rocky asteroids, densities typically range from 2 to 3 grams per cubic centimeter, similar to common minerals. For icy bodies, pure water ice has a density near 1 gram per cubic centimeter. But comets almost never achieve this. Measurements of cometary densities, when possible, typically yield values between 0.4 and 0.6 grams per cubic centimeter, less than half the density of solid ice. This porosity is fundamental to cometary structure. It means that more than half the volume is empty space. The nucleus is not a solid block, but a loose matrix, a sponge of ice grains and dust particles with voids between. This structure explains many observed properties: the low mechanical strength, the ability to absorb impacts without shattering, the ease with which gas can percolate from the interior to the surface during outgassing. A porous structure is almost required for something that formed by gentle accretion in the outer protoplanetary disk. For 3I Atlas, density cannot be measured directly. That would require knowing both mass and volume. Volume can be estimated from brightness, assuming a size and albedo. But mass requires observing gravitational effects, the way the object deflects other bodies, or how it responds to forces. For an isolated comet in deep space, no such measurements are possible. The density must be assumed or inferred from indirect evidence. Researchers typically assume cometary densities fall within the known range for solar system comets, somewhere between 0.3 and 0.7 grams per cubic centimeter. This assumption allows volume to be estimated from brightness measurements. If 3I Atlas has a similar density to typical comets, and if its brightness corresponds to a certain size, then its volume follows. But the assumption might be wrong. An interstellar object formed in a different stellar system might have undergone different processing. The porosity might be higher or lower. The density might fall outside the typical range. High porosity creates interesting structural possibilities. If half or more of the volume is void space, then what appears as a single nucleus might actually be a collection of smaller components with large gaps between. The gaps are filled with loose dust and granular ice, but not in a way that provides structural continuity. In such a configuration, the concept of multiple centers becomes ambiguous. Is it one porous body or many fragments barely touching? The distinction depends on how connectedness is defined. Some researchers model comets as fractal aggregates. At small scales, ice grains stick together to form pebbles. Pebbles accumulate into boulders. Boulders collect into larger structures. At each scale, the packing is inefficient, leaving voids. The result is a hierarchy of empty spaces, from molecular scale pores to meter scale cavities. Such a structure has no single density. The density varies with the scale of measurement. A small sample might have higher density than the average for the whole nucleus. This fractal perspective suggests that looking for discrete multiple centers might be the wrong question. Instead, the nucleus might be better described as a continuous but highly heterogeneous medium, with density varying smoothly or in patches throughout the volume. Some regions are denser, more cohesive. Others are looser, more fragile. Outgassing might preferentially occur from the loosest regions, where gas can escape most easily. These would appear as bright spots in the coma, mimicking multiple active nuclei without requiring discrete separation. Only took 1 trillion grains of ice to build something this ambiguous. Each grain represents a separate accretion event, a moment when a drifting particle encountered the growing nucleus and stuck. Over millions of years, these moments accumulated into a structure, but the structure retains memory of its construction. The internal architecture reflects the randomness of accretion, the haphazard arrangement of components, the voids created when grains didn't fit perfectly together. The result is not engineered, but evolutionary. Not designed, but emergent. There's also the possibility of internal cavities. As a comet approaches the Sun and begins outgassing, gas generated deep in the interior must escape. It flows through the porous matrix toward the surface. If the flow encounters a region of higher resistance, perhaps a denser layer or a narrow channel pressure builds. The gas seeks alternative paths. Over time, it may erode channels and cavities within the nucleus. These subsurface voids can be substantial, meters or tens of meters across. When such a cavity is located near the center of the nucleus, it might register as a region of lower density, a void within the mass distribution. If multiple cavities exist, the nucleus effectively has multiple centers in the sense of having multiple density minima. This is a very different structure from a contact binary or rubble pile, but it might produce similar observational signatures. The mass distribution is complex. The outgassing patterns are irregular. The brightness varies in ways that suggest multiple sources. Distinguishing between these scenarios requires data that doesn't exist for 3i Atlas. Radar observations could probe the interior, revealing subsurface structure and density variations. But radar requires either close proximity or very powerful transmitters and sensitive receivers. For an interstellar object at several astronomical units, radar is infeasible. Spacecraft flybys could measure gravitational variations as they pass different parts of the nucleus, mapping the internal mass distribution. But organizing a flyby mission takes years, and 3i Atlas is already leaving. so the internal structure remains conjectural. Models can propose configurations consistent with the data, but consistency is not uniqueness. Multiple models fit equally well. The porosity could be uniform or variable. The voids could be small and distributed or large and localized. The density could range from 0.2 to 0.8 grams per cubic centimeter depending on location within the nucleus. All of these are possible. None can be confirmed or eliminated. There's a certain appropriateness to this uncertainty. The interior of any celestial body is hidden from direct observation. Even for Earth, the deepest drills reach only a few kilometers into a planet thousands of kilometers in radius. Knowledge of Earth's interior comes from indirect methods: seismic waves, gravitational measurements, magnetic fields. For 3I Atlas, even these indirect methods are unavailable. The interior remains dark, inaccessible, knowable only through inference and assumption. And inference, when data is sparse, produces multiple possibilities that coexist in an uncomfortable superposition. The journey between stars is long beyond human comprehension. 3I Atlas has been traveling through interstellar space for at minimum tens of millions of years, possibly much longer. During this time, it has experienced conditions fundamentally different from those in any planetary system. No sunlight, no solar wind, no planetary perturbations. Just the cold. Thin medium between stars and the gradual erosion that comes with it. The interstellar medium is not empty. It contains roughly 1 atom per cubic centimeter on average, mostly hydrogen. In denser molecular clouds, the density increases to hundreds or thousands of atoms per cubic centimeter, along with dust grains and complex molecules. An object moving through this medium at typical interstellar velocities, tens of kilometers per second, collides constantly with these particles. Each collision is minuscule. A single hydrogen atom carries negligible momentum, but over millions of years, trillions upon trillions of collisions, the cumulative effect becomes measurable. The leading surface of the object erodes. Atoms in the ice matrix are sputtered away by impacts. The process is extraordinarily slow. Estimates suggest erosion rates of perhaps a few centimeters per million years, for an object several hundred meters across. This represents a negligible loss over even 100 million year journey. But the erosion is not uniform. The leading surface, the hemisphere facing the direction of motion, experiences more impacts than the trailing surface. This creates asymmetry, a directional weathering that might subtly reshape the nucleus over deep time. Cosmic rays present another source of modification. High-energy particles, mostly protons accelerated to near light speed by supernovae and other energetic events, permeate the galaxy. When a cosmic ray strikes the nucleus, it penetrates deep into the ice, ionizing molecules, breaking chemical bonds, creating radicals and new compounds. This radiation processing alters the chemistry. Some molecules are destroyed, others are created. The color of the ice might change, darkening as complex organic compounds form from simpler precursors. The depth of cosmic ray penetration is limited. Most energy is deposited in the outer meter or so of material. Deeper layers remain relatively pristine, protected by the overlying ice. This creates a stratification, a radiation-processed crust surrounding a more primitive interior. When the object approaches the sun and begins outgassing, the outer layers sublimate first. The processed material is lost. Deeper, less altered ice is exposed. The chemistry of the coma might change over time as different layers become active. For 3I Atlas, The ratio of processed to pristine material depends on how much has been lost during previous perihelion passages in its home system and how long it has been in interstellar space. If it's a dynamically new comet one that has never been in the inner regions of its home planetary system, the entire surface might be radiation processed. If it has orbited its parent star multiple times before ejection, the processed layer might have been stripped away already, exposing fresh ice. The observations don't distinguish between these histories. Interstellar dust presents another hazard. While most interstellar material is atomic or molecular, small, solid grains also exist. These are typically submicron in size, but even small grains carry significant kinetic energy at interstellar velocities. A grain traveling at 50 kilometers per second has the energy of a rifle bullet, despite its microscopic size. Collisions with such grains can create tiny craters, ejecting material, gradually sandblasting the surface. The cumulative effect of these collisions over millions of years is uncertain. The impact rate depends on the density of dust along the trajectory, which varies greatly. In the diffuse interstellar medium, dust density is extremely low. An object might go thousands of years between significant impacts. In denser regions, molecular clouds, the outskirts of stellar systems, impacts become more frequent. If 3I Atlas passed through such a region during its journey, the erosion could be substantially greater than average. Only took 30 million years of absolutely nothing happening except slow decay. The object drifts. Atoms strike its surface. Cosmic rays alter its chemistry. Occasionally, a dust grain impacts, creating a small crater invisible from Earth. The temperature remains stable at 10 or 20 Kelvin, cold enough that molecular motion nearly ceases. The ice is glassy, amorphous, locked in a metastable configuration. No sublimation occurs, no activity, no change except the inexorable erosion measured in atoms per second across a surface area of square kilometers. There's also the question of volatile loss. Even at the temperatures of interstellar space, the most volatile ice is hydrogen. Helium cannot be retained. Their sublimation rates, though astronomically low, are non-zero. Over millions of years, these molecules escape into the void, one by one. Slightly less volatile species, like carbon monoxide, might be retained in the coldest regions, but lost from warmer areas. Water ice, the least volatile of the common cometary components, remains stable indefinitely. This differential loss might create compositional gradients within the nucleus. The outer layers, slightly warmer due to cosmic ray heating, lose volatiles faster than the interior. The surface becomes depleted in carbon monoxide, enriched in water ice and refractory organics. The interior retains a more primordial composition. When outgassing begins as the comet approaches the Sun, these gradients reveal themselves. The first gas released might be water-rich, sublimating from the processed surface. Later, as deeper layers are exposed, carbon monoxide becomes more prominent. Some researchers study the desorption rates of various molecules at different temperatures. Laboratory experiments freeze gas mixtures onto cold surfaces and measure how quickly they evaporate as temperature increases. These measurements provide benchmarks for modeling cometary behavior, but the conditions in these experiments, hours or days, controlled temperatures are vastly different from the conditions in interstellar space millions of years. Uncertain temperatures, cosmic ray bombardment. Extrapolating laboratory data to interstellar timescales requires assumptions that introduce substantial uncertainty. The internal temperature of the nucleus during interstellar transit is also uncertain. Cosmic ray heating deposits energy throughout the volume. Radioactive decay of trace isotopes like potassium-40 or uranium-238 provides another heat source. Though the contribution is small for objects this size, heat conducts slowly through porous ice. The interior might be slightly warmer than the surface, though still well below 50 Kelvin. This temperature difference, maintained over millions of years, could drive slow diffusion of volatiles from interior to surface, gradually homogenizing the composition or creating unexpected concentration patterns. All of this processing erosion, radiation damage, volatile loss, thermal evolution occurs invisibly during the long dark passage between stars. When 3I Atlas arrives in the inner solar system and becomes observable, it carries the cumulative imprint of this journey. But disentangling the effects of interstellar processing from the effects of formation and pre-ejection history is nearly impossible. The object's current state is a palimpsest, multiple histories written atop one another, each layer partially obscuring the others. What defines a center, ultimately, is a question that sounds philosophical until it becomes practical. In classical mechanics, the center of mass is well defined, the point where the mass distribution balances, where gravitational force can be considered to act. For a solid, uniform sphere, this point lies at the geometric center. For an irregular object, it might be offset. For a contact binary, it lies somewhere between the two lobes, possibly in the neck region, possibly an empty space if the lobes are widely separated. But for a porous, heterogeneous object like a comet nucleus, the concept becomes less clear. If density varies throughout the volume, the center of mass might not correspond to any particular physical feature. It's simply a mathematical point derived from integrating mass over volume. And if the object consists of multiple loosely bound components, each component has its own center of mass. The system as a whole has a barycenter, the collective center of mass, but asking whether this represents one center or multiple centers depends on how the question is framed. Observers looking at 3I Atlas see brightness distributions in the coma. These distributions suggest multiple sources of outgassing. Each source could be interpreted as a center in the sense of being a distinct active region, but active regions need not correspond to structural separations. A single nucleus can have multiple vents, each producing its own jet and coma condensation. So the appearance of multiple centers in the coma doesn't necessarily imply multiple physical nuclei. The mapping from observational signature to physical structure is not one-to-one. Some researchers define a center as a region of locally maximum density. In a porous rubble pile, there might be several such regions, places where components are more tightly packed, where the local density exceeds the surroundings. These density maxima could be thought of as cores within the larger structure. If they're sufficiently distinct, separated by lower density material, the object effectively has multiple centers. But if the density varies continuously, without sharp boundaries, then identifying discrete centers becomes arbitrary. The structure is better described as a gradient than as a collection of components. There's also a dynamical definition of center related to rotation. An object rotating as a rigid body has a well-defined rotation axis passing through its center of mass. But if the object is not rigid, if different parts rotate at slightly different rates, then the concept of a single rotation center breaks down. Parts of the object might be rotating around local axes that don't coincide with the overall center of mass. This is more relevant for very loosely bound systems, where components are gravitationally held but not in physical contact. For 3I Atlas, whether such differential rotation exists is unknown. In planetary science, the distinction matters for practical reasons. Mission planners designing a flyby or landing need to know where the center of mass is located to calculate trajectories. Scientists modeling outgassing need to know whether gas comes from one nucleus or several to interpret activity patterns. But when observations are insufficient to determine structure, these practical needs remain unmet. The object exists in a state of definitional ambiguity, simultaneously describable as one thing or as multiple things depending on the chosen criteria. Only took 100,000 years of philosophical debate to not resolve this question. Or rather, the question has never been posed this way before because never before has an object like 3I Atlas been observed with sufficient detail to raise the question while maintaining insufficient detail to answer it. The sweet spot of partial knowledge that generates maximum uncertainty. Enough information to recognize that something interesting is happening, not enough to understand what. There's a concept in physics called coarse graining. When describing a system, the level of detail depends on the scale of observation. At atomic scales, water is discrete molecules bouncing chaotically. At human scales, it's a continuous fluid with well-defined properties like density and viscosity. Neither description is wrong. They're appropriate for different purposes. Similarly, 3I Atlas might be one object at the scale of kilometers, multiple objects at the scale of hundreds of meters, a collection of countless grains at the scale of millimeters. The question, does it have multiple centers, has no absolute answer. The answer depends on the scale at which center is defined. This kind of scale dependence is common in astronomy. Galaxies appear as single objects from intergalactic distances, but resolve into billions of stars when viewed up close. Nebulae seem continuous from afar, but are revealed as complex structures with filaments, clumps, and voids at higher resolution. Even planets are not truly uniform. Earth has a crust, mantle, and core multiple layers with different properties. At some level of detail, everything is composite. The question is whether the composite structure is relevant at the observational scale. For 3I Atlas, the observational scale is limited by distance and instrument resolution. Ground-based telescopes see a fuzzy coma with internal structure. Space telescopes might resolve slightly better, but still can't image the nucleus directly. The observations capture structure at scales of hundreds or thousands of kilometers, the extent of the coma, but not at the scale of the nucleus itself, which is likely only a few hundred meters across. So the question of whether the nucleus has multiple centers at 100-meter scales remains inaccessible. Some researchers argue that the terminology itself is problematic. Terms like multiple nuclei or multiple centers imply discrete separation that might not exist. Better to describe the observations neutrally, the coma shows complex brightness morphology consistent with multiple active regions. Whether these regions correspond to separate physical bodies or to heterogeneous activity on a single body remains undetermined. This phrasing is more accurate but less evocative. It doesn't capture the peculiarity of the situation as effectively. Language shapes thought. By asking, does it have multiple centers, the question presumes that centers are discrete, countable things, but physical reality might not conform to this presumption. The nucleus might be better described by a continuous density field with multiple maxima and minima, or as a hierarchical structure with organization at many scales simultaneously. Forcing this complexity into a binary yes or no question inevitably loses information. Yet binary questions are what humans prefer. The mind seeks categorization, classification, the comfort of discrete labels. 3I Atlas resists this comfort. It occupies an uncertain space between categories, neither clearly one thing nor clearly multiple things. The observations suggest complexity without revealing its nature. The models permit multiple interpretations, and the language available for description is inadequate to capture the subtlety of what might be happening. So the object remains, in the scientific literature and in the minds of those who study it, a question mark. A reminder that the universe is under no obligation to organize itself according to human conceptual frameworks. What remains unknown about 3I Atlas exceeds what is known by a considerable margin. This is not unusual in astronomy. Most celestial objects are understood only partially, through fragmentary observations that constrain some properties while leaving others entirely uncertain. But for 3I Atlas, the imbalance is particularly stark. The object has been visible for only a few weeks at adequate brightness for detailed study. During this window, observers have extracted every possible measurement, pushed instruments to their limits, accumulated data that fills databases and forms the basis for dozens of research papers. And still, fundamental questions remain unresolved. The size of the nucleus is uncertain to within a factor of 2. Estimates range from 200 to 500 meters in diameter, depending on assumed albedo and shape. The mass is unknown except through assumptions about density. The rotation state is partially characterized but ambiguous. The internal structure is entirely conjectural. The formation history is inferred but not constrained. The trajectory before entering the solar system is calculable backward only to a point, beyond which uncertainties grow exponentially and all directions become equally plausible. Even the composition, which is the most directly observable property through spectroscopy, remains incompletely characterized. Water and carbon monoxide are clearly present. Other molecules are suspected methane, ammonia, carbon dioxide, formaldehyde, but detections are marginal or absent. Isotopic ratios, which could provide strong constraints on formation environment, are at the edge of measurement capability. Some teams claim detections of deuterium enrichment or carbon-13 variations. Others find the signals consistent with noise. The debate continues in the technical literature, each side presenting analyses and counter-analyses. The question of structure, the central mystery that motivated the initial interest, remains open. Is it one nucleus or several A-contact binary, or a rubble pile, or a monolithic body with complex surface activity? Each interpretation has proponents. Each can point to aspects of the data that support their view. None can definitively rule out the alternatives. The situation is not uncommon in science, particularly in fields like astronomy where experimental control is impossible and observations are limited by distance, brightness, and time. Some researchers express hope that future observations might resolve the question. Perhaps 3I Atlas will brighten unexpectedly as it continues outward, allowing extended observation. Perhaps some aspect of its behavior, a sudden outburst, a fragmentation event, a change in rotation state will reveal internal structure. But these are hopes, not predictions. The object is fading steadily as it recedes from the sun. Each passing week makes observation more difficult. Within months, it will be too faint for all but the largest telescopes. Within a year, it will be undetectable. There's also the possibility that archived data, reanalyzed with better techniques or computational tools, might yield new insights. Observations made during the brief visibility window are stored in digital archives maintained by observatories and space agencies. These archives persist indefinitely. Future astronomers, with access to improved modeling algorithms or machine learning techniques, might extract information that current analysis misses. The data itself is a resource that outlasts the observation opportunity. Only took a few weeks of visibility to generate decades of analysis work. This ratio is typical for transient astronomical phenomena. supernovae, gamma-ray bursts, gravitational wave events. The actual observation window is brief, but the scientific exploitation of the data continues for years. Each time a new theoretical model is developed, it can be tested against archived observations. Each time computational power increases, more sophisticated simulations become feasible. The initial observations are just the beginning of a long process of interpretation and understanding, but some questions may remain permanently unanswerable. Without higher resolution imaging, the structure of 3I Atlas cannot be directly resolved. Without mass measurements, density remains assumed. Without isotopic measurements of sufficient precision, formation environment remains loosely constrained. These limitations are not temporary, awaiting better technology or more observing time. They're fundamental, imposed by the object's distance, brightness, and velocity. The opportunity to observe has passed. What is known is all that will ever be known from direct observation. This finality is difficult to accept. The human mind prefers problems that can eventually be solved, questions that might be answered given enough effort or time, but astronomy frequently presents questions that remain unresolved not because of lack of effort, but because of lack of accessible information. The universe is vast. Most of it is far away. Light carries limited information. And some objects, like interstellar visitors, pass through the observational window so quickly that comprehensive study is impossible. Some researchers frame this as an argument for preparedness. If another interstellar object is detected early enough, with sufficient warning, observations can be planned more carefully. Multiple telescopes coordinated. Spacecraft missions considered, though the timescales for mission approval and launch are long, but even with perfect preparedness, fundamental limitations remain. A comet nucleus a few hundred meters across, several astronomical units away, cannot be resolved in detail from Earth. The physics of light diffraction sets absolute limits on what ground-based telescopes can achieve. There have been proposals for rapid response spacecraft missions, small, lightweight probes that could be launched quickly, designed to intercept interstellar visitors during their passage through the inner solar system. Such missions are technically feasible but expensive and require advanced preparation spacecraft already built, waiting for a target. The cost of maintaining this readiness for uncertain payoff makes the proposals difficult to justify. And even if such a mission were successful, it would observe only one object. The next interstellar visitor might have entirely different properties. So, the knowledge remains fragmentary. 3I Atlas joins the small but growing list of interstellar objects detected passing through the solar system. Each detection adds to the statistical sample, gradually building a picture of what exists in the galaxy, what configurations are common or rare, what processes operate in other stellar systems. But each individual object retains its mysteries. The sample size grows slowly. Decades might pass before enough interstellar objects have been observed to draw strong general conclusions. In the meantime, 3I Atlas recedes. Its brightness drops below the detection threshold of most instruments. Tracking continues with the largest telescopes for as long as possible, squeezing out final data points to refine the trajectory, searching for late outbursts or unexpected behavior. But mostly, the object returns to darkness. The brief moment of visibility ends, and the scientific community moves on, attention shifting to the next discovery, the next anomaly, the next question that might, with sufficient effort, yield an answer. The archive preserves what was seen. In databases maintained by observatories, space agencies, and research institutions, the photometric measurements sit in standardized files. Timestamps, brightness values, uncertainties, spectroscopic data arranged in tables, wavelengths and intensities, emission lines and absorption features, astrometric positions tracking the object's motion across the sky, each position representing a moment when photons from 3i Atlas struck a detector and were recorded. This is the permanent record of the encounter, the complete observational history encoded in numbers. These archives are not static. They're regularly queried by researchers, downloaded, analyzed, incorporated into new studies. A graduate student writing a thesis on interstellar objects pulls the 3i Atlas data, combines it with observations of other visitors, looks for patterns. A theorist testing a new formation model extracts specific measurements to compare with predictions. An observer planning a campaign for the next interstellar discovery reviews past observations to optimize strategy. The data continues to work, to generate insights, long after the object itself has faded from view. But archives are also fragile in ways that physical objects are not. Data formats change, storage media degrade, institutions reorganize, merge, disappear. Without active curation, digital archives can become inaccessible within decades. The file formats become obsolete, the documentation is lost. The data persists as bits on a disk somewhere, but the ability to interpret those bits, to transform them back into meaningful measurements, erodes. This is digital decay, slower than physical decay, but equally inexorable. Some scientific organizations recognize this threat and work to preserve data long-term. Standards are developed, migration strategies implemented, archives are replicated across multiple institutions to reduce the risk of loss. Metadata is carefully maintained so that future researchers can understand what the numbers represent. This work is unglamorous and underfunded, rarely resulting in publications or grants, but essential for the long-term health of the field. Without it, observational astronomy becomes amnesia, each generation starting fresh, unable to build on past work. For 3i Atlas, the data is currently well preserved. Multiple teams observe the object. Each maintains their own archive. The observations are also submitted to central repositories like the Minor Planet Center, which tracks all small bodies in the solar system and beyond. The redundancy provides resilience. Even if one archive is lost, others survive. But this redundancy requires coordination, standardization, agreement on formats and protocols. Not all observations are shared publicly. Some remain in personal repositories, on laptops and external drives, vulnerable to accidental deletion or hardware failure. Only took 100 terabytes of storage to capture everything observed. This sounds like a lot, but by modern standards, it's modest. Consumer hard drives hold multiple terabytes. Cloud storage services offer similar capacities. The data from 3i Atlas could fit on a few commodity hard drives, making physical preservation trivial. The challenge is not storage capacity, but organization, accessibility, long-term curation. Raw data is useless without the metadata, calibration files, and documentation needed to interpret it. There's also the question of what constitutes the complete dataset. The observations themselves are just the beginning. Calibration data measurements of reference stars, instrumental characteristics, atmospheric conditions are equally important. Analysis pipelines. The software used to process raw data into scientifically useful measurements must be preserved to allow reanalysis. Publications describing the observations, methodologies, and conclusions add interpretive context. All of these components together form the full record, and all must be preserved for future utility. Some researchers advocate for data reanalysis as a standard practice. When new techniques are developed, old data should be reprocessed to see what was missed initially. For 3i Atlas, this might mean applying machine learning algorithms to detect faint structure in images that human analysis overlooked, or using improved atmospheric models to refine spectroscopic measurements, or combining observations from multiple telescopes in ways that weren't attempted originally. The potential for new discovery exists in archived data, waiting for the right analytical approach. But reanalysis requires effort, and effort requires motivation. Grants typically fund new observations, not reprocessing of old data. Publications favor novel results over incremental improvements. The incentive structure of academic science pushes researchers toward the new and unexplored rather than the thorough and careful. As a result, much archived data is never revisited. It sits in databases, technically accessible but practically ignored. A resource whose value is recognized but not realized. Occasionally, a particular object or event becomes the focus of renewed attention. A new theory predicts a specific signature that might be present in old data. A comparison study requires historical measurements. An anniversary prompts reflection on past observations. In these moments, archives are interrogated. Data is extracted and analyzed, sometimes yielding surprises. A feature that seemed like noise is revealed to be signal. A measurement dismissed as anomalous fits a new pattern. The old becomes new again through the lens of better understanding. For 3i Atlas, such moments might come. Perhaps in 10 years, 20, 50, a researcher studying interstellar object populations will pull the archived data, looking for trends across multiple visitors. Perhaps a new instrument will detect another object with similar properties, and comparison will be needed. Perhaps a theoretical breakthrough will suggest what to look for in brightness fluctuations or spectral features, and the 3i Atlas data will be reanalyzed to test the prediction. These futures are possible but uncertain, contingent on developments that cannot be foreseen. And if no such moment comes, if the data sits in archives unused for decades or centuries, does it still have value? Arguably, yes. The preservation itself is valuable. Maintaining the possibility of future insight, even if that insight never arrives. Like ancient texts in library archives, rarely consulted but irreplaceable. The data represents a record of what was, a connection to a moment in time when an interstellar visitor briefly brightened and was observed. The value is not purely utilitarian. There's also an archival impulse, a desire to preserve knowledge for its own sake. Independent of immediate application, the universe doesn't wait for human readiness. Objects pass through, events occur, opportunities come and go. Those that are observed and recorded enter the archive. Those that pass unnoticed leave no trace. Over time, the archive grows, an accumulating record of what humanity has managed to see and measure. 3i Atlas is now part of that record, a small addition to the vast catalogue of celestial phenomena. Its mysteries, resolved or unresolved, are preserved in data, waiting for whoever might, someday, look again. The object moves outward now, beyond the orbits of the inner planets, heading toward the realm of asteroids and then onward to Jupiter's domain and beyond. The outgassing slows as temperatures drop, the coma thins, disperses, eventually dissipates entirely. What remains is the nucleus itself, dark and cold, returning to the state it maintained for millions of years before entering the inner solar system. The brief activation is over. The ice returns to silence. Telescopes lose track of it gradually. First, the smaller instruments can no longer detect it. Then the mid-sized observatories. Eventually, only the largest telescopes, given enough integration time, can find the faint point of light against the background stars. And then, inevitably, even these lose it. The object becomes too faint, too distant, indistinguishable from countless other faint sources in the sky. The tracking ends not with dramatic conclusion, but with simple, fading, signal dropping into noise, the object returning to invisibility somewhere in the outer solar system. 3i Atlas crosses the heliopause, the boundary where the sun's influence gives way to interstellar space. This transition is gradual, unmarked by any physical change to the object itself, just a mathematical boundary in the density of particles, the strength of magnetic fields. The object continues on its hyperbolic trajectory, velocity unchanged, direction set. It will not return. The orbit is not closed. This was a single pass, a brief intersection of paths between one stellar system and another. The galaxy continues its rotation. Stars move through their orbits around the galactic center. In a few million years, the sun will be in a different position, surrounded by different neighboring stars. 3i Atlas will be far away, drifting through some other region of space, possibly passing near other stars, possibly remaining isolated in the vast gaps between them. Its structure, whatever it is, will persist. The configuration will remain frozen, preserved by cold and isolation, unless it encounters something a close stellar passage, a collision with another interstellar object, an unusually dense molecular cloud. It will continue unchanged. There is no narrative arc to this, no resolution, no climax, no denouement, just motion through space, the slow drift of matter through void. The questions raised by its passage remain questions. The ambiguities remain ambiguous. This is often how astronomy works. Objects appear, are observed, provoke inquiry, then fade before inquiry resolves. The universe is not constructed for human understanding. It simply is, indifferent to whether its mechanisms are comprehended. In archives, the data waits. In journals, the papers describe what was seen and what remains unknown. In the minds of researchers, the memory of 3i Atlas persists as one among many objects studied, one puzzle among countless others. The field moves on. New observations demand attention. New questions arise. But occasionally, in moments of reflection or comparison, 3i Atlas returns to thought. The object that might have had multiple centers, or might not have. The visitor that challenged categories and then left before providing answers. The ice drifts outward. The stars turn slowly overhead, their position shifting imperceptibly night after night. And the mystery, such as it is, remains suspended in the cold dark between stars, carried by an object no one will ever see clearly, no one will ever fully understand, no one will ever observe again. Just data and questions, archived together, waiting in the vast patience of deep time and empty space. Sleep well.